Relating E potential cell with the free Gibbs energy. Okay, so delta G for the redox can be found by using this equation. Delta G is equal to minus NFE, where N is equal to number of the mole, the electrons transferred. F is the constant, the Faraday, which is the value is 96,500 coulomb per mole. We got one equation here. E cell is equal to minus RT over NF ln Q. This is one equation of from the Gibbs. Right, so next. Okay, next we look at on factor affecting the E cell. First is position of ion in the standard reduction potential, or SRP. So you have to look at where is the ion position. Is it above the hydrogen or below the hydrogen? Is it reduction? Is it oxidation? So you must know where is their position. Normally, the one that have higher potential, for example, imagine the waterfall just now, so it has higher potential of the different value of the higher and lower, that gonna affect your E cell. E cell will be more or E cell will be less, let's say. Alright, and then concentration of the ion in the electrolytes. Dilute concentration gonna give you different electrode potential. More concentration also will give you different electrode potential values. So concentration does play a big role in the electrode potential cell. Temperature, number 3, temperature of the reaction, yes, also play the important role. Let's say you put of your electrolyte in a hot bath, for example, that's going to influence the rate of ion transferred, and of course in the end it's going to influence the E cell potential. Okay, and then pressure of the gas when the reaction involves gases, especially hydrogen. When it's involved gases, of course pressure will play a lot of role. If you put under pressure, basically the ion potential, the E cell will be different as well. Okay, so this one, all these factor, we can put it in one, and then we can represent it by Nernst equation. So you have looked at Nernst in the in the thermodynamics before. It's just the same. Alright, so we have delta G is equal to delta G naught plus RT ln Q. This means if we change with delta G with NFE, what you got is minus NFE is equal to minus NFE naught plus RT ln Q. This is the same one. Okay. Now we divide both equations, left and right, by minus NF. Okay, when once we divide, this minus MF will be cancelled out. What remaining is E cell, and then this one is what remaining is E naught cell. Okay, and then we still have this one minus, it's become minus now because we minus by NF here or here. Okay, that's why it's changed to minus. So RT minus over NF ln Q. This is come out a new equation of Nernst. And then we prolong it. If you use the base 10 logarithm, okay, which is equal to 2.302 log A is equal to ln A. When we have ln A RT here, so you replace the value with this value, it come out with new equation. So this is a new equation. Alright, so you don't have to worry much how to derive the equation. You just take the final equation. So T is equal to temperature, R is ln gas constant, which is this value 8.314, and then F, this is the value 96,500. N is your number of mole of electron in the equation that you times up both half equation, how many electron that has been lost or gained. Okay, alright, and then Q basically the concentration. This is a concentration of who? Concentration of the products over the reactant. Okay, and then it's always power of X or power of Y. Power of X or power of Y here meaning that coefficient number of the respective product and the reactant. If you have the final equation of your half cell equation just now, you have to look at how many products, how many coefficient. Let's say it produces 2 Na plus 2 Cl. Okay, that will be coefficient that will be put here. Okay. Okay, so at room temperature, we know that is equal to 298 Kelvin. You can change this, okay, times room temperature to 98 Kelvin. You're going to get this value, 0.0592 volt. That equation, now we rearrange into Nernst equation, we can get this final equation. E cell is equal to E naught cell minus 0.0592 over N log Q. Okay, so this one from the Nernst equation, when we replace log Q with the concentration of product over the concentration of reactant, this is the final equation that you have to. So this is the final equation that you have to remember. Okay, so look at how concentration play a role in the voltaic cell. Okay, so you can look at here. What we have here, we have the same one, nickel. Okay, a nickel as the anode and a nickel as the cathode. Then same goes to this one, nickel, anode and cathode. Okay, but what the difference here? The difference here, you have different concentration. You have what the difference here is. What the difference? Okay, so this one. Okay, this one, the difference here is a concentration. This one is very dilute. 1 time minus 3, 1 time minus 3. But this one is more concentrated, 1 molar. Okay, so meanings, you still, when you have the same electrodes, same electrode for anode and cathode, though both are coming from nickel, but this one is anode, this one is cathode, but you have different concentration of electrolyte, still you can get reading here. Okay, still you can get reading up here, where it give you, when a voltaic cell using the same substance at both electrode, E cell will be 0, but E cell will not be 0 as long as the concentration is different, though you have the same electrode. See, the same electrode, different concentration, the E cell still can be read. But if you have same electrode, both nickel, both similar concentration, 0.5 molar, 0.5 molar, what you got is 0. So it's impossible to measure the concentration, the potential. Okay, right. Equation, this one. 2 chromium. Who is a product? Product is chromium 2. And then reactant is 3 from the stannum. Okay, over 3. That's why. Okay, alright. So that will give you please solve all these. Solve the log first and then solve the rest. So you're gonna get 0.6395. That's equal to 0.64. It's only two significant figures. Okay. So now we're gonna see. Yes, I told you how if I told you sometimes that we have concentration in the P. It's involved hydrogen electrode where it's involved gas. Okay, at 1 atm for example. So how are we gonna use the log Q that's involved P? So this is an example. Right. So now you have a new reference electrode. Chemists construct a voltaic cell consists of zinc over zinc 2 plus and then hydrogen to H plus, half cell under following condition, calculate the E cell. So you are given these three concentration, 1, 2, 3, zinc, hydrogen and pressure of the hydrogen in atm. Look at this is molar, this is atm. Focus, please focus this one. So first thing first, you have to write the half equation for both. Okay, you have zinc and hydrogen. So what you need to do, zinc, you may write with who first, zinc or hydrogen, and then look at to the SRP, who gonna be anode, who gonna be at cathode. As we know, hydrogen is higher than zinc, so hydrogen would be reduction. Okay, hydrogen would be reduction and zinc would be oxidation. So zinc from reduction is this one. This is reduction from SRP for hydrogen is correct. No need to change. Okay, no need to reverse anything because it's seated above the zinc. Zinc somehow it's going to be anode. So once anode is zinc. For reduction is zinc 2 plus 2 electron produce zinc. But somehow you need to reverse it because it's become anode now. So once we reverse it, zinc becomes zinc 2 plus 2 electron and the E cell has to be reversed as well. Okay. If you use the formula, the correct formula, you have to reverse. If you use the other formula, you don't have to reverse. Okay. Alright. Again, find the final equation. This is the final equation. Now, what you're going to do, you have to do the Nernst equation. E cell is equal to E naught cell minus 0.0592 volt over N log Q. N is 2, correct? N is 2, yes, N is 2. E naught cell is the final of these two. Okay, final of those two, how many the value is? And Q now, product over reactant. Your product is zinc and hydrogen. Hydrogen here is involved because it's been stated here, reference electrode and hydrogen gas. Okay, alright, so it gives you the value as well, 0.3 atm, so it has to be included. And the pH2 adalah potential hydrogen times by concentration of zinc over the hydrogen. Normally this is in gas, this is in aqueous. Okay, so yes, look at this one is gas, this one is aqueous. So next, that is Q. So next you settle this 0.3 atm times by this one molar. So this one H2 is involved 2 here because we have 2 hydrogen. The rest are not involved any coefficient, don't need to put. Okay, so now find the final Q. Q is equal to this one. No unit needed. Although this one is molar atm, no unit needed. So okay, just put 4.8 times minus 4. Okay, next put it in insert here. Okay, 4.8 10 minus 4. Right, N is equal to 2. E cell is positive 0.76. Okay, so final value is 0.86 volt. Okay, alright. So the same one, it gives you concentration. Okay, so you have to do how to do it. First thing first, it gives you concentration from argentum to argentum. This one, same as this. Okay, for this one, I want to emphasize log Q. Q is product over reactant. Or if you have just like this, you are given the value here. You can put Q is equal to dilute concentration over concentrated one. Who is more dilute, put it up. Who is more concentrate, put it down here. So dilute here, minus 4 here is much more dilute compared to 0.01. Alright, so N is equal to 1. E cell you have to find from the equation. Is it given? What is the cell potential? Okay, you have to find the cell potential. Okay. Okay, so this one is not given, so put it as 0. Okay, 0.0592 over 1 minus times by log that. Settle that one. First, the value is 0.0828. Okay, make it into 3 significant figures. So I want you to do this exercise. Okay, do exercise here. Calculate the concentration. It's just the same. Use the Nernst equation here. Okay, well this one. Okay, so this one probably because we have H2 aqueous, but then this one is liquid. So yes, try use the same Q of reactant or product over reactant. Product over reactant to calculate the concentration. Take a break here. So next we're going to continue how to find Kc from the Nernst equation.